one of the 4 data inputs. So it will take one of the 4 data inputs and pass it to the output, depending on the so-called select input that you apply. So if your select input, in this case it's a 2-bit select input because it has to select one of the 4 possibilities. And if the select input is 0, 0, it will take whatever you give here and will pass it to the output. If it is 0, 1, it will be cloud instances with FPGAs available from major cloud providers, which allow you to make use of cloud-based acceleration. Just like how there are instances with GPUs available. Yeah.
Those architectures for parallel computing is better than FPGA, but they can still be followed over the ASIC design.
Yes, they can be. Yeah. Typically, if your volume is not so huge, your incentive to create an ASIC might not be
But it
very
was
huge.
cheaper and faster to port those architectures over those circuits over ASIC.
Possible. I mean, porting over anything to ASIC will still require a lot of work beyond just the logical part, the physical design part, etc., etc. So it's not like it's so easy to take an FPGA design to ASICs. Okay, there is still a lot of tools involved. There is a lot of verification involved downstream for ASICs, which typically are a lot easier for. Okay, and then again, your volume needs to be big enough to justify that effort. And in many cases of custom acceleration, it's not. Like for example, Microsoft Bing search engine runs on FPGAs. Not a great search engine, but well, it is accelerated using FPGAs, and there are several such applications. And FPGAs do have capability to do partial reconfiguration, fault tolerance, etc., which make them kind of attractive in scenarios where you want possibly slightly lower performance when some parts of the circuit fails. Like for example, failure of a transistor or a logic gate can be mitigated to a good extent by reconfiguring it to avoid that part. And some FPGAs do have the capability to have some part of the FPGA running while some other part gets reconfigured, which is what we call partial reconfiguration. Okay, it can provide desirable features such as fault tolerance or graceful degradation in performance. Like for example, you can have a trailer where a blown tire does not necessarily mean the trailer will be stuck in the road. It can still probably continue, but at a lower speed. Okay, so same thing for circuits. Your performance might go low, your functionalities could reduce, but it's not an abrupt one, because if you have enough of a volume to justify it, and certainly lower power for a given computation. But you cannot suddenly make it to perform another computation if you wish. Like for example, if you create an ASIC for a particular blockchain, okay, where the blockchain validation algorithm is a certain way. If you suddenly change the algorithm, you cannot use the same platform anymore. Like for example, now Ethereum is changing their scheme, right, from proof of work to proof of stake. So a lot of changes will have to be made, which ASICs can't really deal with. So that's a flexibility efficiency trade-off that I was talking about. So typically for the same functionality, the amount of silicon required will be about 35 times. And the speed is typically 3 to 4 times lower. An ASIC typically runs at gigahertz range, let's say 2 gigahertz. A typical FPGA based accelerator runs at 100 to 400 megahertz for the most part.
Is it because FPGA critical path is usually higher?
Yes, very good in fact. Yes, that flexibility increases your critical path. You see, you can decide how to configure a logic block, how to interconnect them, etc. Right? So that flexibility requires switches and other stuff to be introduced in between, which will inevitably increase your critical path. And surprise, more than 80% of the FPGA resources are dedicated to routing, not to logic. So that programmable interconnections is what takes up most of the resources of FPGA. So that's why it is suited for low volume products, prototyping, verification, emulation, etc. And of course, it also requires, I would say, more trained manpower. So it's becoming less the case with the advent of modern tools such as high-level synthesis tools. Okay, so we had seen the hardware design flow, we had seen the architectural logic and physical synthesis steps. Then we had seen that synthesizable HDL is a subset. We also saw that we had to keep the hardware in mind while writing our HDL code or while doing anything related to hardware design. And testing on hardware is really the last step after you have exhausted all your other testing options. And we also saw FPGAs are highly configurable hardware, well suited for prototyping. And with that, let's move on to the next chapter, next part of the chapter. Get started with it before we go for a break. Even though it's titled Verilog for synthesis, a lot of things are not just about Verilog. It's about good hardware design practices in general. And if you follow good design practices, and if you write the corresponding Verilog code, it will naturally and automatically be good. That's it. So some rules for synthesizability. You must have used stuff like this in Verilog. This means delay by 10 simulation steps. And if your simulation precision is like so-called nanoseconds, you are delaying it by, let's say, 10 nanoseconds. The simulation. But it doesn't make any sense when it comes to synthesis. You cannot tell the tool, I want the signal to go from here to here in or within 10 nanoseconds using HDL. You can do that to some extent using design constraints. But HDL code cannot explicitly specify any kind of delay. Because HDL code for the most part is hardware independent. It doesn't even matter whether you are targeting an FPGA or ASIC. Most of the HDL code is the same. It can even be exactly the same depending on how you write it. Generally, again, if you try to make it generic enough, you are possibly compromising on optimization. But yeah, it's entirely possible to write HDL code in such a way that it's very portable across tools and platforms. So combinational delays are hardware independent. It's not something the synthesis tool can insert based on HDL code. It's controllable to some extent through constraints. And these design constraints are more tailored to the target platform. It's given in your .xdc file. Xilinx design constraints. I don't know whether they will change it to ADC now that it is AMD. But it's based on the industry standard .sdc format. Synopsys design constraints. Synopsys is one of the big, or if not one of the biggest electronic design automation tools. In fact, the XDC file allow you to specify constraints such as, okay, the delay between A and B should not exceed, let's say, 0.5 nanoseconds. But this again is a suggestion. If the tool really can't do it, it will come back and give you a critical warning saying some timing constraints are not satisfied. And that means you are trying to do something which is too much to ask from the tool. And you probably need to go back to the drawing board and make essential changes. So anyway, the point is that you cannot have hard-coded delays inserted through HDL. That's the bottom line. Cycle delays can be inserted too. So here I am talking about combinational delays that can be inserted. But if you want a cycle delay between point A and point B, it's easy to achieve. Just insert registers. One register being inserted means that a change in A will be reflected in B only one cycle later, only one clock edge later. And assuming A itself was changed as a part of a clock edge, B will change only at the next clock edge. So you are essentially introducing one clock delay between A and B. And that is very much a part of your design. And remember, registers are something which you design, you specify the position of through your HDL. Okay, so you can introduce physical registers and it's not done automatically by the synthesis tool based on delay. Remember, synthesis tool does not insert or remove or change registers. It will only optimize combinational logic between registers. So, for example, here, if x is a value which changes like this, and x was changed immediately after the clock, the corresponding change will be reflected at z only at the next clock edge. So you can see one cycle delay is introduced, and this is done by writing code. And we will see more coding examples on how to write code for this, but in this case it's very simple enough. Now next step or next recommendation, try to use only one clock for your entire design where possible. Well, real world designs do have different parts running at different clock cycles, but that is at a much bigger level. So when you are creating a module or something, have only one clock. Having multiple clocks, it brings in a lot of trouble. You require more clocking resources because clocks are not connected using conventional wires. Clocks are typically routed through some dedicated clocking resources or trees. Because clock is a very, very important signal which ideally should reach every part of your circuit at the exact same time. And that will require you to have very dedicated wires to carry clocks in a design. And multiple clocks means you need multiple such wires or so-called trees, because clock is distributed as a tree. It comes from a main spine, goes into different areas and then split into different areas. Ideally in such a way that at all endpoints or leaf nodes it reaches at the same time, ideally. So anyway, different clocks means you require more resources, and it complicates your timing analysis, because eventually once the synthesis is complete, the tool will do some timing analysis to see whether it really satisfies the timing constraints that you put in. Like for example, if you specify that your clock frequency is 100 megahertz or your clock period is 10 nanoseconds, your critical path should be no more than 10 nanoseconds. So it will analyze every combinational path to see whether it fits within 10 nanoseconds. Otherwise it will give you warnings, not errors, warnings. So this timing analysis process becomes more complicated if you have more clocks to deal with. Yeah, and timing analysis itself is a fairly complicated process, again very computationally complex, and you are making it even worse if you have more clocks. And if you have different unrelated clocks, you need specialized circuitry to do clock domain crossing. Like for example, if you have one part of the circuit which is run from one oscillator, another part of the circuit run from another oscillator, even if their frequencies are the same, they will not be in sync for very long, because there are always uncertainties with real world clocks. So even if they started at the same time and runs at the same frequency, after a few clocks or few tens or hundreds of clocks, they will go out of sync. So if you are trying to combine the two outputs in some manner, the outputs may not change at the same time.
Is it required to using one operator and then scaling down the signal say like I know how many circuits require the one from another one requires one.
Good question. I was about to mention that even if you require different frequency clocks, you typically do not use different oscillators for that in a single system. Like for example, in a computer system, your processor might be running at something like 3.6 megahertz. Your RAM module might be running at, let's say, 1300 or 1400 megahertz. Right? And they have to exchange data, possibly in a synchronous manner. How can it be possible if they are driven using totally unrelated clocks? No. You cannot have any kind of synchronous transactions. And then the data from one unit to another unit has to be considered asynchronous. You cannot rely on any timing relationship at all. And such asynchronous transfers do come with a lot of complexities and typically compromise on speed possibility. So that's why within a computer system, a lot of transactions, at least within the motherboard, are mostly synchronous transactions. How are they achieved? How can you get different frequencies which have definite time relationship with each other? Typically these frequencies, base frequencies, are generated by some crystal oscillator which runs at something like 33 megahertz or 100 megahertz. 33 is a very typical frequency. And then you multiply it with a certain multiplication factor to get the final frequency. Like for example, if your CPU is supposed to run at 3.3 gigahertz, you take 33 megahertz and multiply it with 100, right? And if your RAM is supposed to be 1333 megahertz, you do 33 into some factor. Whenever you have, when you have time, you can do the computation. But it will scale it up with a certain factor and use it using frequency multipliers. And frequency multipliers are accomplished using a very, very interesting circuitry called PLLs. Anyone heard of PLLs before? Yeah? If you have taken a module on analog design, you would have heard about PLLs. Phase lock loops. The way it works is quite interesting. If you are interested, try to read it. So that's how computer systems have different clocks while retaining synchronization. Now, the clock should not come from a combinational circuit if at all you end up using multiple clocks. You can use a counter with some kind of modulus to scale down a clock, to divide it. To multiply, you will of course require something like PLLs. To scale down, you can use counters. Like for example, if you need to reduce the frequency by a factor of 16, you can just use a mod 16 counter. Yeah? But the output should be taken from a sequential element, not from a combinational element. For example, the most significant bit of a counter, still okay. Because the counter most significant bit itself comes from a flip-flop, not from a combinational circuit. At any rate, do not have a combinational circuit giving clock. So for example, you write certain code, which is meant to do a combinational circuit like this, and then feed it as a clock to a sequential circuit. Your results can be quite funny because your combinational circuits can have so-called glitches. Okay, this is a fairly meaningless circuit, but just to illustrate the concept of glitches very fast. So let's say your your input is low. What is your output Z supposed to be? Supposed to be low, because you see, when input is low, okay, let me write 0 instead. This is 0, this is 1, this is 0, and the output is 0. Now let's say if your input is 1, this is 0, this is 1, your output is still 0. So you are essentially looking at a circuit whose output is supposed to remain 0 no matter what the input is. Which is why I said it's a bit meaningless, but it's easy to illustrate the concept of glitches using this, and that's why I chose this circuit. Now let's say your input now transitions from 0 to 1. So originally, Okay, let me write the original scenario using green color. This was 0, this was 1, this was 0, this was 0. Now this 0 transitions to 1. Here, assuming that this wire is having no delay at all, this becomes 1 immediately. But does this go to 0 at the same time? No. There is a gate, it has a delay. So, before it becomes 0, you are looking at a scenario where it's momentarily 1 1. And an input of 1 1 to an AND gate could cause your output to be momentarily 1 before it stabilizes back to 0. So after a while, this 1 really goes to 0, and that will cause your output to be back to 0. But in between, you could have a small output, or your output with a relatively small width or time span, which is not what you desire or expect. This is what we call a glitch. And this glitch could act as a clock for this circuit, which could mess up the operation of that. And you will end up with a behavior which is not what you expect. Again, this is a simplified picture, but you see the problem, right? So do not have a combinational circuit driving a clock. You know, some of you I had seen had used in your previous modules. You possibly got away with it, but don't do it all the time. Yeah.
Is this why the errors don't show up the simulation waveforms, but when what about the FPGA and the simulation?
Very well. Yes. You know, this is one scenario where your simulation might not show any issue at all, but your hardware may not work. Yeah. Then do not use oscillate, negate for anything other than clock or reset of a sequential process. So if you want to see whether a button is pressed, whether a button has an edge, don't use something like a posset button. Posset, negate, etc. are to be used only with clock signals. So how do you know whether there was a press or not? Let's say you have a button. You want to detect whether it was pressed or not, assuming press means going from low to high. How do you know? You need a specialized circuitry for that, rather than just doing something in HDL. So the circuitry looks kind of like this. Okay, so this will be Q bar. So I didn't say it should be Q bar. Okay, sorry, I forgot that part. This date. Yeah. So if it is Q bar, then how does it work? So let's say when this is 0, this will be 0. Okay, this will also be 0. So your button edge, that is whether there is an edge for the button, is 0. When the button is pressed, this becomes 1. Sorry, wait a minute. Your output is 0, so Q bar is 1. So 1 and 0 will be 0. That's the original situation. Yeah? Because when your input is 0, this flip-flop will be storing a 0, so Q bar will be 1. Q bar is a complement of what you store. So that will be 1. So this is 1, and this is 0 because the button was not pressed. At the point when you press the button, this will become 1. This will not become 0 immediately, it will become 0 only at the next clock edge. So you have a scenario where your output is 1. That's how you detect whether there was an edge or not. So this is what we call a synchronous edge detection scheme. So what we do is, we store the old value of button, or we store the value of button at every clock edge, and keep it stored until the next clock edge. So this part is essentially to implement this flip-flop. Or you can think of it this way, here there is a NOT gate. It's the same thing. Okay, so this flip-flop is this part. Now this part, which is looking at the node of the flip-flop output with the button input is this. So you store the button previous value, which won't change immediately when you press a button, right? So if the button was not previously pressed, this will be 0, so node of that will be 1. And at the moment when you press the button is also 1, so you detect it as an edge. And a small while later, that is, when you have a clock edge coming in, this will change to 1 and this will change to 0, right? When you have the next clock edge, that level of the button is captured. Once it is captured, well, this becomes 0 because the captured value will be 1, so node of captured value will be 0, so this will go back to 0. So you are able to capture the press of the button. So this will be true only for a short while, that is from press until the next clock edge. That's ideal. So this is how you do asynchronous edge detection. Anyway, not particularly important for this module, but I included this so that you get the idea that, okay, this is not how you detect whether a button was pressed or not. You detect a button press by looking at whether it was 0 previously and now it is 1. Then you see that there is a change, there is a press. And to store that so-called previous value, you require a flip-flop. So once again, my mistake, my bar here, there should be a NOT gate here, or consider this as Q bar, and correspondingly a tilt side here. Then last point, do not have combinational feedback paths. Is such a circuit sensible? You can see your value of A depends on value of Z, but value of Z itself depends on value of A.
What is you consider a case for
Yeah, it will be something like a large, depending on whether it will stabilize or not. But yeah, normally for your standard designs, this kind of connections are not okay. Your synthesis tool will give a warning or error depending on your setting that you have combinational feedback path. Okay, and for most FPGA with synthesis tools, the default is error, not warning for this. What is the problem here? Your output depends on the current output depends on current input, but current input itself depends on current output. So you are essentially looking at a circular logic, right? Which in most cases does not really make sense, but there is one specific case where it actually makes sense. Like you mentioned, this kind of a configuration is actually used in the creation of latches, and flip-flops, but that's another story. But something like this is okay. So that feedback path is broken by a register. So you see, this value depends on this, but not in an instantaneous manner. So a change here does not cause a change at the output immediately. That input is captured and transferred to output only at clock edges. In between, any change to input does not change the output instantly. So that circular logic is in some sense broken. But of course, these two are not identical with respect to functionality. And chances are that if you ended up with something like this, you probably do not know what you're doing. Okay, so it's meaningless to talk about functionality in the first place anyway. So you see, this is a circular logic. This is a combinational feedback path. Your Z is combinationally dependent on A. A is combinationally dependent on Z. Combinationally because this is a combinational always block. Whereas here, you see, it's not a combinational always block. This, in fact, describes this circuit. this is described by this. So this is a sequential part with some combinational aspects as well, but considered sequential. So yeah, let's stop here. We have a few more slides to finish this chapter, and then we will get started with the next, but after a 15 minutes break. So let's come back for maybe 10 minutes. Come back here by 7:45. Procedurally assigned, like for example, those which are assigned within an always block or initial block. Whereas if you are assigning using an assign statement, which is what we call a continuous assignment, we use wires. Continuous versus procedural assignment. Right? Procedural blocks are always and assign. Sorry, always and initial. Whereas continuous blocks are assigned. Now, recs and wires should not have multiple drivers. So, a rec or a wire should not be assigned at two different places. For example, if you look at this code, always at start, which is a when you look at always at start, you are essentially looking at a combinational circuit. In this, Z is assigned A and B. In another always block, you are assigning X or Y to Z. So what is the equivalent hardware? How will it look like? It will look like this. Does it make sense? Okay, let's say A is 0. Let's say B is 0. Let's say X is 1. Y is 1. What is the value of Z? Anyone? So obviously this will be 0 and this will be 1. What is the result? Well, this kind of a connection is illegal, right? There is no point in talking about results because you are not supposed to do it, right? What will happen to you if you run across the expressway? Well, it's a meaningless question because you are not supposed to do it, right? So same thing here. Now, if you look at how these circuits are designed, you will realize that 0 means a low resistance path to ground. Okay, so this is almost like a connection to ground. This is almost like a connection to, plus whatever VCC or VDD. Now you are essentially connecting a VDD, a high voltage, directly to a low voltage. What will be the current between the 2 points? The potential here is, okay, let's say we are looking at a 3.3 volt device. The potential here is 3.3. The potential here is 0. So the potential difference is 3.3 volt. And the resistance between the 2 points is almost 0. So what will be the current? Positive infinity, right? You are looking at a huge current, which will result in an explosion if they are ideal voltage sources. Okay, which is indeed what will happen if you power it using a lithium-ion battery. It can explode, but usually, the transistors involved will burn out first before an explosion happens. But yeah, it could result. At least technically, it could result in an explosion. So anyway, this connection is completely meaningless and illegal. And the same thing would happen if it is assigned using assign statements. You could always, for combination circuits, you could always write assign Z is equal to A and B. But of course, if you are using assign, then Z should be declared as a wire. Whereas if you are using it inside always, it should be a rec. But a rec does not mean it's a register. here I declared it as a reg, but it's not a register. Okay, that's one of those, I would say, sad mistakes made by Verilog designers. Calling something a reg and causing a lot of confusion. Because a reg does not necessarily translate to a physical register. Yeah, a reg is something which is simply assigned within a procedural block. It doesn't mean it becomes a register, and in this case, it doesn't become a register anyway, even without the mistake that you made. But yeah, trying to connect it together is having multiple drivers, which again will show up as an error. But it's okay to have a reg at LHS of multiple statements within the same always block, as long as the same type of assignment is used. So here you can see I have an example where I am assigning a value to z as 0. Then if x is false, if x is 0, then I am assigning assigning y to z. Is it meaningful? Yes. The circuit that will be generated from this code will look like this. You are in some sense saying, okay, z is 0 except for the condition when x is not true. And when x is not true, z is y. So when x is 0, z is the same as y. Whereas when x is 1, this is 0, so this is 0 no matter what y is. Right? So this makes perfect sense, and it's okay to have z appearing on the left hand side at two different places within the same block. But if it is at two different blocks, we have problem. Such a scenario should not happen. Now, is it possible that in real world you have scenarios where sometimes the value of z should be this, sometimes the value of z should be this? Can happen, right? Then how do you fix that problem? Well, not by connecting them together, by having a multiplexer too. Okay, you need to have a multiplexer. One input comes from here, another input comes from here, and you need a select input which will select one of the two depending on the scenario, depending on which one should be affecting the output at that point of time. Yeah, so that's how you resolve that contention, not by connecting them together. Now back here, the point is that you can assign within the same block without issue, and it does translate to something meaningful and something quite okay. Functionally, the last assignment will determine the value of reg after the always block execution. So in this particular case, if x happens to be true, that is not of x is not true, this will not execute, and then z will be 0, which is what you want. So basically when x is 1, not of x is 0, so not of x is not true, so this has to be 0. So this part assignment will not happen. So you see that this code translates to something meaningful in hardware. So this is synthesizable. Whereas this translates to something which is not meaningful in hardware, and that's why it's not synthesizable. Good idea, right? And this is why I was mentioning earlier that if your mental picture is correct, you will end up doing something which is correct. But if you are not sure what you are doing, you will end up with something like this. And then it could show up as a warning or alert, but if you ignore it, you will have trouble later. Now, next part, initialization of regs. Regs can be initialized through an initial block. Initial is very similar to always, except that always gets triggered whenever there is an event at any of the inputs in the sensitivity list. Like for example, here it is always at star. So whenever something can affect the output changes, the output is re-evaluated. Whereas here, always at percent clock means your output is re-evaluated whenever there is a positive edge of the clock. So this part is what you call sensitivity test. And this is an always clock. Initial clock is very similar except that it has no real sensitivity list. It is triggered only once when the simulation starts. Okay, which is kind of similar to how things are initialized at power on when the hardware is switched on. Or for FPGAs, when a new bit stream or configuration is loaded. Then everything starts over, right? That's initial. So if you need to do any initializations, you can put it in initial block. But you can also do it by doing an initialization along with the declaration of that reg. So I can write as reg z is equal to 0. You initialize z to 0. Yep. But initializations are not meaningful for wires. Initializations are meaningful for only regs that become real registers. Wires cannot become real physical registers, whereas some of the so-called regs become physical registers. And we will see a bit more about it soon enough. Yeah. But the point is, when you initialize something, it becomes or it is meaningful only when whatever you initialize is supposed to hold something. That is, it has some kind of a memory, which is either a memory or a register. Initializing something which is not a memory or a register makes no sense. That's what I am trying to say. And even these initializations that you do are sensible only for simulation and only for synthesis for FPGA tools. ASIC synthesis tools totally ignore any initialization that you do. So just because you write reg z is equal to 0 does not mean when you power on z is indeed 0. A flip-flop, without any additional circuitry, can have its output at a random 0 or 1 when you power on. There is no guarantee that when you power on a flip-flop, it will be having an output 0. So if you want to guarantee that it turns on and the output is 0 at turn, if you want to guarantee that the value at power on is 0, you need to add explicit circuitry for that. And this is one such mechanism. So when you power on, or just before you power on, what will be the voltage across the capacitor? Basically 0, right? And that will cause the reset to be asserted. So at the instant when you power on, the capacitor will still be at 0 volts. I mean, the potential difference across it will be 0. That will essentially be pulling this down, and this is a reset input, an asynchronous reset. Some flip-flops do have asynchronous set and reset. So that will cause your output to be 0. What will happen after a short while? So initially the voltage across the capacitor is 0, but it will gradually increase, and at some point it will increase enough for it to be taken as a logic 1. And a logic 1 for an active low signal will make it inactive. So your reset is essentially released, and your flip-flop is free to store a value synchronously based on whatever you give here. Got the idea? So this kind of an analog or RC circuit is required to assert a reset asynchronously so that you can fix the value at power on. Just by writing a code like this, it will not synthesize a relatively complicated circuit like this. And this again is a simplified version of a reset circuit. It sort of works. Okay, there is more sophisticated versions used in real world circuits. Good idea? So it does not really translate like this for ASIC. but for FPGAs, it does. FPGAs do have a dedicated mechanism to set initial values of all memories and registers, called a global set reset mechanism. And hence, all these initialization values are respected by FPGA synthesis tools, but ignored by ASIC synthesis tools, because FPGAs do have built-in circuitry for that. For ASIC, there is nothing built in because you are building it, right? So it does not get automatically built because you mentioned something like this.
But
This. Yes, of course, you can implement the circuits in ASIC, but totally separately. This part is not even digital. Yep. Now, wires cannot be meaningfully initialized as they don't store anything. Because wires are, well, wires are combinational circuits. They don't store anything. So, initializing it makes absolutely no sense. Because initialization is meaningful only when something is stored, right? So, wires don't store anything, so no initialization. But if I write something like wire z is equal to 0, is it illegal? No, it's not. It will just create a wire which is permanently connected to 0, which is almost certainly what you are not expecting or intending, right? So initialization to 0 or 1 will connect the wire to a constant 0, 1 or 1 respectively. And later, when you do something like, say, assign some z is equal to something else, now we have a multiple driver issue, because it's permanently connected to 0, but now we are trying to connect something else. So 0 as well as something else become drivers for that particular wire. Okay, so you have a multiple driven net issue or multiple driver issue. Now, RECs that get synthesized as combinational circuits cannot be meaningfully initialized. We will see this later that not everything REC becomes a register. Some of them in fact become combinational circuits and they cannot be meaningfully initialized. And do not assume that registers and memories will have 0 initial value. So these are some general recommendations. There are more, but these are based on some of the typical mistakes that people make. Now, there are 3 templates that I have provided, which, if followed, will make your life a lot easier. So, whenever you create an always block, make sure that it follows one of the 3 templates. First is a purely combinational circuit. What is a purely combinational circuit? One where all outputs are sum of product or product of some expressions of the current inputs, instantaneous inputs. Rules are, every input must be present in the sensitivity list. So if you are describing a combinational circuit, all inputs for the combinational circuit or to the combinational circuit should be present in the sensitivity list. Or you can simply put star. I personally prefer to put the inputs very explicitly where possible, because that makes your code a bit more readable. Just by looking at the block, you can clearly identify what are the inputs, whereas always at star is not very readable, right? It is like whatever affects, but it will not tell us what affects. We have to scan through the code to figure out what all are the inputs. Whereas if you list it explicitly, well, it makes it a bit more readable. And also, if you accidentally use something which you are not supposed to, you will at least get a warning. Okay, so I personally recommend not using star, even though, of course, even I myself use it sometimes when I get lazy. But yeah, try not to. Okay, another possibility is use assign statements. Unless your combinational circuit is very big, you can typically express it using assign statements. Okay, like for example here, it could have been quite easily done using assign statements, like assign z is equal to note of x and y. quite possible. But if your circuit is very complicated, then assigned statements become very long and less readable, in which case always blocks are the preferred way to go. Now, what if you miss out one of the inputs? Like for example, in this case, what are the inputs in reality? X and Y, right? Because I am trying to describe, let's say something like this. If my Y appears on the right hand side, it means Y has an influence on output. So Y should be an input. So it should be in the sensitivity test. But I put in only X, I missed out Y. You will typically get a warning. And that warning is a very important warning to know. Yeah, because your simulation in this case will be giving you wrong results. But luckily, synthesis will most likely be correct. Because synthesis tool is a bit smarter. It will figure out that you accidentally missed it out. So it will do you a favor by including it automatically and will give you a warning. But it will still cause the simulation and synthesis results to be mismatched. Because it's not the same functionality that the two tools deal with. Synthesis tool won't have the functionality to compensate for your mistake. Yeah. Now, second, so that's a prop point. Now, what is a functional issue with this? If you miss out Y, Y was supposed to affect output, but now in this, Y does not affect output instantaneously. At some point in time when Y changes, without an accompanying change in X, so that is Y alone changes, your output doesn't change. So input has changed, output doesn't change, even though that change in input was functionally supposed to affect the output. Which essentially means your output is memorized. A change in Y was supposed to change output, but based on your code, it doesn't. Which means the code is trying to describe something which memorizes output for some time at least. And whenever something is memorized, you are not looking at combinational anymore. So what you are getting or what you are describing is actually not what you are intending. That's a problem. You get the idea? So here, if X and Y are there, if there is a change in Y, this whole thing will be re-evaluated, so that will change. But now look at a scenario where Y is forgotten, and then when Y changes, X does not change, and only a change in X will cause output to be re-evaluated. So that change in Y does not cause output to be re-evaluated. So output doesn't change, according to the behavior of the code. Whereas your intention was for output to change, right? So the behavior of the code is that the output doesn't change, and for something not to change, it has to be memorized. And if you have memory, it's no longer combination, which means it's not what you intended. That's the problem. Now, next, very important point, probably the most common mistake of all. Every rec must be assigned a meaningful value for every possible input combination. So every rec should have a meaningful value for every possible input combination. So if there is an if, there has to be an else, implicitly or explicitly. And here, you can see that is forgotten. Now let's say I fix the first issue. I included Y. So first point is okay. Is it still okay, or is it still having issues? It still has issues, because if X is not true, if X is low, Y is what Z will be, or Z will get the value of Y. But what if X is high? That is, when not of X is not true. Your code does not describe that scenario at all. Your code does not specify what your output should be when input is 1. So functionally, the result is that your output does not change. So the functionality of your code is that the output does not change in the scenario where this if is not true. That is when x is 1, not of x is not true. And then the value of z will be retained or stored. And for your output to retain its value in spite of a change in input is essentially memory. For something not to change, it has to be memorized. And then again, what you get is not combinational. See the problem? So yeah, we need to have every reg assign a meaningful value for every possible input combination. That is for all branches of if or case statements. Now we had a scenario here where there is no else. But I said it's okay. Now why is it okay? Even though I do not have an explicit else, I am having an implicit else here. I am having a value assigned to z, then modified in a certain circumstance. In the other circumstance, it's not modified, but it is still a defined output value. So that else is implicit. So either implicitly like this or explicitly like this, you need to have an else. That's the point. Otherwise, your synthesis tool will try to create something called a latch. A storage device which does not require echo, which is a latch. And again, your functionality that you get will be different from what you intended. Okay, probably the number one reason why there is a mismatch between simulation and synthesis. Now the last point is not particularly important if you put star. Okay, but if you write things explicitly, like for example in this case x and y explicitly, then the last point becomes important. A rec appearing on both LHS and RHS within an always block should appear on LHS before RHS. Now what exactly is that? So if I have a code which looks like this, so let's say z is assigned a value a. Now before I can do this, I need to assign a value to a. So it should appear on the left hand side before it appears on the right hand side. So that I am assigning something temporarily and then using it. What if it is the other way around? What if I am using a value before giving a value? Then I am using the old value. And whenever I say old, I am in trouble in the context of combination circuits. Because to have something old, it needs to be memorized. So I am inferring memory here. You see the problem? Now a reg assign using non-blocking assignment should not appear on the right hand side of the same block. So if I am assigning it using non-blocking like this, then z should not appear on the right hand side again. The point is, z will get the value only after the always block has completed execution. It's called non-blocking because z is destined to or scheduled to get the value of a after the execution. So subsequent statements within the same block does not look at the updated value of z. It has to remember the old value of z. And remember, old means trouble. But this is not an issue if star is there in the sensitivity list, because the always block will be triggered over and over and over until the output is fully evaluated. Now, second template is for synchronous circuits. A synchronous circuit is a circuit where output changes only on the rising or the falling edge of a single clock. So only post edge or neg edge clock should be present in the sensitivity list. So basically, we are looking at a circuit where your output changes only at either the rising edge or at the falling edge of a clock. Basically an edge triggered circuit. And depending on the edge that it is sensitive to, only that edge clock should be present in the sensitivity list. So either post edge clock or neg edge clock. And only regs that change on the same edge of the same clock should be assigned in the always block. So basically, anything that is assigned in the always block should be those signals which change state at the same time, which is all triggered by the same clock. So if you have mechanisms whereby, well, you have one positive triggered clock, one negative edge triggered part. So some circuitry here, some circuitry here. These two should not be combined into a single always block. Because many synthesis tools look for a single clock for an always block. If they see multiple clocks, well, you might be in for trouble. Which is especially made worse by the fact that Verilog does not have a proper level triggering mechanism. Verilog does not allow you to combine edge and level triggering. Okay, so if you have post edge here, all these should have some edges, and that makes it problematic. Now, next, use non-blocking assignments for outputs of the always block as well as for any internal physical register. So whenever you are intending to store some value in a register at that clock edge, use non-blocking assignments. For example, here, the value of Z is the only value that is to be stored, that is to be registered. So Z should be assigned using non-blocking assignment, which is exactly what I do here. And keep in mind that the updated values are not available for use at the same clock edge. So a change in Z is not something that can be used at the same edge. So if this is the edge that causes Z to change, Z in reality changes only just after the clock. Which means at the clock edge it is not available for processing, or the updated value is not available for use. Now there is another way to infer registers. So if you want to insert a register, one way is to have non-blocking assignments within a synchronous always block, an always block with a post edge or neg edge clock. The other way is to read something before you write. Like for example, if inside this you had a scenario where you had something like, say, A is equal to something, but then A appears on the right hand side first. Is it okay? Here I had mentioned that it is not okay, right? I had mentioned that it should appear on the left hand side before right hand side. Whereas here it is appearing on the right hand side before left hand side. Is it okay? In this case it's okay, because the value of A that is used here will be the old value of A, which means the value of A is memorized. And here memory is not troublesome at all, because we are indeed describing circuits which have memory. So it's okay. Whereas in the other case it was not. And here you are inferring a memory for A. But inferring memory this way, while functionally perfectly okay, is not a fantastic practice simply because it's not very readable. Yeah? And there are circumstances where doing this way alone is not sufficient. But let's not go into those details. But anyway, try not to do this way. A better way to implement registers is non-blocking assignment within an always block, within a synchronous always block. Now, you can use blocking assignments for, or you should use blocking assignments for internal combinational parts. So for example here, this temp is essentially the signal that appears here. So this is essentially the output of a combinational part within a larger sequential block. And assign it using blocking assignment so that the updated value is indeed what you store. Which is how it should be, right? Because it's connected by a wire. And in this case, it should appear on the left hand side before it appears on the right hand side. Otherwise it's memory, it's not combinational. But it's not a bad idea at all to take out this combinational part separately and implement it as a separate block. To have a cleaner separation of combinational and sequential parts, which can make things less confusing, but which can make your code a bit longer than it should be. So that's a purely synchronous circuit. And when you are doing FPGA design, there is no reason why you should deviate from either of these two templates. Okay, but for ASIC designs, sometimes you do have scenarios where you need asynchronous set or reset. And I already mentioned that scenario, right? Typically to do a power on set or reset. And in that case, how will you write the code? All the rules pretty much, or what you had here, pretty much applies here too. Slight deviations or differences, posage net edge clock and posage net edge set or reset should be present in the sensitivity list. So here you see, there is an asynchronous reset. When the reset is applied, your output goes to 0 immediately without waiting for a clock edge. Whereas this is a synchronous input. D has an effect on output only at clock edges. So the effect is synchronous. Whereas here, the effect is asynchronous. The moment you assert reset, output is 0. No clock required at all. And this is typically used for power on initializations like the one I had explained earlier. And then you have posage clock if it is positive edge triggered, and if it is active high reset, then posage reset. But here it's a bit of an aberration, right, from the real meaning. Reset is something which is supposed to have an effect whenever reset is asserted. It's a level, not an edge. Unfortunately, Verilog does not allow you to combine the two. So without this is not okay, even though that's what you actually intended. Okay, so that's why VHDL is a semantically poor language. But yeah, well, we are stuck with it, so yeah, not sure it's really. Now, you get the point, right? So we need to have posage reset if it is positive, if it is active high reset, which is how it is here. If it is active low, you will have a bubble here. Then it would have been negative reset. And inside the if statement, so the first thing that we do is if reset. Oh, by the way, there was another mistake here in the notes uploaded. I have corrected it. There was one N missing. Now, inside the if statement, the output should be assigned a vector of zeros and ones. Nothing more should be done. So here you see if reset, then Z is 0. Don't do anything else here. Only assign a vector of ones and zeros. And here it's a single bit, so I assign a 1 or a 0. If I had assigned a 1, it would have been a preset. If it is a 0, it's essentially a clear, both asynchronous. So here I am implementing an asynchronous clear. And that's all you should do here. Don't do anything more. Everything else should be done inside the else. This is a synchronous part. And this is the asynchronous part. So inside the asynchronous part, do only an assignment to ones and zeros, and everything else should be inside the synchronous part. All other logic. Yeah. So all other code should be inside the else of the if else. There should not be additional ifs or else ifs. So the structure should be if reset, then do the asynchronous part, which is assigning a vector of ones and zeros. Else, everything synchronous. There should not be any outer else if, else if, else if, else kind of stuff. Okay, there is just if asynchronous, else synchronous. That's it. It is fine to have additional ifs inside the synchronous part though. So for example, inside it, it's perfectly fine and it's perfectly normal to have an if. And it doesn't even need an else. Why? Why is else not necessary for that internal if? Yeah, it is synchronous. So if there is no else, the value will be retained. The value will be memorized. And that's perfectly okay. Because we are indeed describing circuits with memory. Okay, unlike combinational circuits where else was mandatory, because we need to have an output specified for every possible input combination. We cannot expect the output to remain or be retained as such. Whereas here, that expectation is perfectly okay. You can expect the output to not change. That will require memory, but synchronous circuits have memory. It's okay. Now, this is a design, or this is something you need to avoid wherever possible. There is no reason why you should use this in FPGA designs, because FPGAs do have initialization mechanisms in place. There is no reason for asynchronous set or reset. Yeah.
But there is a state machine box, and you want one block to reset another block to prepare it for, say, a data transfer.
You can do it synchronously. It will incur a cycle delay, but that's okay. That's how you should design it anyway. So what if you want a reset? Well, that reset should be designed in such a way that it has a synchronous effect. It should also wait for clock. In which case, this part should also go inside here. Okay, this part should also be inside here. Then it has a synchronous effect. It has an effect only at clock edges. So a change in reset will not have an immediate effect here, which is like your standard flip-flop behavior. That is synchronous trigger. Now there is one point I did not mention here. The typical recommendation for combinational circuits is to use only blocking assignments. But again, because of an issue with Verilog, if there are multiple blocks which are triggered by the same signal, the order of evaluation in simulation can be any order the simulation tool picks up. And sometimes the order of evaluation can have an effect on the simulated output, okay, which is the very infamous unpredictable behavior of Verilog. You can Google about it if you are interested. VHDL doesn't have that issue. Okay, anyway, so you could have a scenario where the exact same code could simulate differently in different simulators. Okay, one workaround which always works for me is to assign outputs using non-blocking. Use blocking for internal calculations, but anything that comes out of the block should be assigned using non-blocking. Then it always works. And it's very easy to see why it works, but again, another story for another day. It's good enough to just follow the practice now without bothering too much. Now, when are physical registers inferred? When we do non-blocking assignments of rec in a synchronous always block. So when you do something like, say, always at something, and then when you do a non-blocking assignment like this, now the value of z is stored in a register. So you can easily tell, right? So that's usually the standard way in which you create registers. There is another way, blocking assignment of reg in the synchronous part, where it appears on right hand side before it appears on the left hand side. So something like A is read first and then a value is assigned in a blocking manner to it. Then A is read before it is written, which means you are reading the previous value of it, which means A is memorized. So here you see you need information retention between clock edges to remember the old value of it. That's why you have a register. Whereas if you do something like this, in the always at postage clock, in a non-blocking manner, why will it infer a register? A is updated at the clock edge. The update happens only a delta after the clock edge. And until the next clock edge, A can't be written. Because clock is the only one which can cause output to change. So here you see, only a change in clock, only a change in clock will cause the output to be re-evaluated. So that output has to retain value until the next re-evaluation, which means the output is registered. Okay, now here there is something which you can read up yourself. Let me not mention it and add to the confusion, but yeah, anyway, maybe I'll just mention it anyway. Yeah, so so what if you don't do this? What if it is a blocking assignment? Will it cause a register to be inferred? Answer is yes, if Z is a value that you use elsewhere. So if this is a value that you use elsewhere, then it will still infer a register, because Z is updated and further or the next update is at the next clock edge. So it has to store value. So it will actually become a register. But again, it can mess up your simulation really badly. So don't do this. If you do this, then the order of evaluation in simulation can affect your result. But it's perfectly fine for synthesis. Remember, synthesis tool is smarter. So it will realize what, or it will figure out what you are trying to do, and it will create a register appropriately. But simulation could be seriously messed up if you do this. Now, why did I say that TMP does not infer a register whereas Z does, if both are blocking? Well, simply because Z is used elsewhere. TMP is immediately consumed, so there is no need to store it. Whereas Z is something which is used elsewhere, so it needs to be stored. Now, having said that, if TMP is also an output, then it also becomes a register even if it is internally used. Okay, but all this can make your code very confusing and very hard to debug, and that's why it's good to follow these templates. Violation of templates could still allow you to get what you want, but you are always taking a risk, and you are certainly making your code difficult to read. Now, if there are two registers that are storing identical content, they could be merged by the synthesis tool as a part of optimization. It's configurable. By default, many synthesis tools like Vivado have the feature enabled, where it figures out that there is one register and there is another register actually storing the exact same thing. They are fed with the same input, or they are fed with inputs which happen to be the exact same logic value all the time. The two of them will have the same value all the time. Then it will realize that these two registers store identical content, and then it will just merge. So if this circuit is feeding another circuit here, here it is feeding another circuit here, it will actually be merged. This will just be eliminated and this will be connected like this. This is a default option. but sometimes during debugging this can get confusing, all these optimizations. So there is a possibility you can turn it off, but by default it's on. Now if a register content is not used in a parent module, it's optimized away along with the combinational circuits feeding it. So here for example, well, you did create a register using this code, but for whatever reason you are not using this anywhere. So this value Z is not connected anywhere. Its value is not used by any other module. Then in the eventual synthesized circuit, this will not be a register. When it does elaboration of design, it will show that it is a register, but later when you look at the synthesized design, it won't be there. Because the synthesis step does optimization. So it will just remove it altogether. And it's not just this which is eliminated, even this will be eliminated. Because the value is not required, so it won't be stored. If it is not stored, it won't be even produced. And now assume that this is fed by another circuit. Now this is no longer used, so this circuit is no longer required. So you could have a snowball effect and you will end up with a design which is much smaller than what you had intended. How do you know whether it's small or not? After synthesis, you can look at the synthesis report to see how much hardware is required. And if you suddenly see that the amount of hardware required is very minimal, very extremely low percentage utilization, you are probably in trouble. If it is too good to be true, it's probably not true, right? Now, we are done. The rest of this chapter is actually for self-reading, and this is a homework exercise. So if you have forgotten your Verilog, you must have realized that it's high time to brush it up, right? So see you all next week, and hopefully without masks.
Yes,